Hi, I'm Rob, and welcome to our fourth lesson in trigonometry. And in our first three lessons, we kind of focused on solving triangles which are right-angled, finding the length of a missing side or the size of a missing angle in a triangle in which one of the angles is 90 degrees. In the next couple of lessons, we're going to look at techniques that will work whether the triangle is right-angled or not. So what happens if the triangle we're trying to solve doesn't contain a right angle, or if we're not sure? So the first one of these techniques we're going to have a look at is the sine rule. So using the sine rule. So the sine rule is a technique for finding a missing side or a missing angle, and it works whether the triangle is right-angled or not. So how can that be the case? How could the triangle work, the sine rule work, if the triangle is not right-angled, because it involves using the sine ratio? Well, if you remember when we're labeling any triangle, okay, that if we call the three internal angles A, B, and C, as we have here, all right, remember that the side opposite those angles are named with the same letter. So opposite the angle A is the side A, lowercase, opposite the angle B is the side B, and opposite the angle C is the side C. So they're the pairings, right? So if you can imagine dropping a line down here to make a right-angled triangle, to tie this in with what we've done over the first couple of lessons, and we'll just call that distance there x, okay? So you'll notice, for example, in this side here, on this triangle here, the only two sides I know the length of are that one there, A, and that one there, X. I don't know how long this one is. I know it's part of C, but I don't know how much of C that is there. So the only two sides I know in this triangle are X and A. And which two sides are they? Well, remember, A is opposite the right angle. That's the hypotenuse. And X is opposite the angle B, so that's the opposite. So opposite hypotenuse means sine. So if I want to write down for that triangle there, the triangle on the right-hand side, it means the sine of the angle B, all right, is equal to opposite over hypotenuse x over A. Okay? And then if I just multiply both sides by A here, so I multiply both sides by A, like that, I'm going to get A times sine B is equal to x. So that's just applying right-angle trigonometry to this triangle here. What about that triangle, the one on the left-hand side? Because again, the only two sides I know there are this one and this one. I don't know how much of C that is. So the two sides I know here, remember, well, this again, that's the opposite. It's opposite the angle A. B is opposite the right angle. That's the hypotenuse. So opposite hypotenuse means sine. So in that triangle there, the sine of A is equal to opposite over hypotenuse, which is x over B. And again, to get rid of the fraction, if I multiply both sides by B there like that, you can see I get B sine A is equal to x. So this here and this here are both what x is equal to. So if these are both equal to x, they must be equal to one another. So I get A sine B is equal to B sine A. And you can see then if I divide across by AB, if I divide both sides by the sides, divide both sides by AB there, the A's will cancel here, I get sine B over B. And over here, the B's will cancel, I get sine A over A. So essentially the idea here, as you can see, and I could do the same thing, I could extend that to show that sine C over C is the same as well. Okay, just by drawing a right-angle triangle, maybe a right angle this way, I make two triangles, one of which has C in there. So the key idea here is you can see if I make the pairs from that triangle, the angle and the side opposite into fractions, those fractions are equal, right? So it looks like that, I mean, you can see there's the first pair, the A's as a fraction, the B's as a fraction, the C's as a fraction, or I can flip it upside down. I can put the sides on top or the angles on top. It depends on what I'm looking for. If I'm looking for an angle, I'll put the angles on top and it'll just save me a line. If I'm looking for the sides, I put the sides on top, but it couldn't matter less. Okay, so that's essentially what the sine rule is. If you take any triangle, whether it's right-angled or not, because the rule is established by using right-angled triangles, but the triangle itself you end up with doesn't have to be, right? So if I'm trying to solve a triangle and either I don't know for sure it's right-angled or I know it's not, okay, the key thing is I don't know it's a right-angled triangle, I can use this method here, and what if I identify pairs, okay, angle and side opposite it, and make those pairs into fractions, those fractions must be equal to one another. That's the sine rule. And to use the sine rule, I must have a pair. So if I'm trying to decide what method to use to solve a triangle, I'm solving a triangle where I know a pair, a side and the angle opposite it. If I know that, it's going to be a sine rule question. So if you look at the first question there on page 43, so the first question on page 43, we've got a triangle that looks like this. Now remember, we spent the first couple of lessons looking at how you solve right-angled triangles, all right? So that's marked as 88 degrees up there. That's marked as 67 degrees down there. And that's 13 centimeters there. and that's the side that's marked x here. So first of all, would I be able to do this by using Pythagoras or by using sine, cosine, or tan? No. Okay, because is the triangle right angled? Definitely not. Do you see how I know it's definitely not? It's not just because there's no right angle mark there. If I add those two together, 88 and 67, I get 155. Subtract that from 180, it means the remaining angle there is 25. So I know for sure there's no right angle in there, so I can't use Pythagoras theorem, and I can't use the sine, cosine, or tan ratios. The only game in town is I have to try and use either the sine rule or the cosine rule, okay? Because they will work whether the triangle's right angled or not. So to pick between them, what I'm looking for now is a pair. Do I know a pair here? Do I know the length of a side and the sides of the angle opposite that? That's what I'm looking for. And you can see in this triangle I do. Because I know the length of the sides of that angle there, and I know the length of the side opposite that. So because I have a pairing like that, that means it's a sine rule question. I can do this with the sine rule. Okay, if I didn't have a pair, so for example, if the side I knew was this side here instead, I know two angles and I don't know the side, although I will be able to find that angle over there, but if I don't have a pairing that I can identify, then it's not a sine rule question. Okay, I'll be working with the cosine rule instead. So for example, if you've got a triangle that looks like that, if you were told, for example, that that angle there is 55 degrees, okay, that angle there, that side's 11, that side there is 12, and that's x. If I ask you to find that, well, is the triangle right angled? The answer is I don't know. It might be. Because if that's the only angle I know, one of those might be right angles. The fact that it doesn't look like a right angle is meaningless. Remember that you don't trust what a triangle looks like. Trust what you know it to be. So the fact that neither of those looks like a right angle doesn't mean that neither of them are. Okay? But in this case, the only angle I know is 55, so I'll have to assume it's not a right angle triangle. So do I have a pairing? Well, I know that's that angle, but not the side. I know that side, but not the angle. I know that side, but not the angle. So I don't have a pairing there. That would be a job with the cosine rule. So that's how you pick between the two techniques we're going to be doing in the next two lessons, and how to choose between the sine rule and cosine rule. Do I have a pairing? Okay, so if the triangle is either definitely not right angled or I'm not sure, I'll pick between one of these two here based on whether I have a pairing or not. So in this case here, I do have a pairing. I know a side and the angle opposite it. And I also then, you can see I'm trying to find this side here. I have the angle opposite that, so there's my two pairings. So what the sine rule means, if I make those two pairs into fractions, I can put those fractions equal to one another. That's all the sine rule is, okay? I can put the sides on top or the angles on top, and because it's a side I'm looking for, I'll put the sides on top here. So let's make this pair into a fraction. So the side on top, so I get 13 on top, and then the angle is 88 degrees. Remember, it's always the sine of the angle. It's the sine rule over the sine of 88 degrees. That's that pairing written as a fraction with the side on top. So that's going to be equal to the other pair written as a fraction with the side on top. That's what your sine rule is. So in this case, the side is x. So it's x over sine 67. And the sine rule just tells you that those two fractions are equal. So identify pairs, write the pairs as fractions, the angles are the sides on top, and then put those fractions equal. That's how we use the sine rule. Okay, and you can see now, as always, to remove fractions, to get rid of the fraction here, if I just multiply both sides here by sine 67 degrees, the denominator here, I'll do that on both sides like that. So multiply both sides by the denominator to remove the fraction like that. And if I do that, on the right-hand side, these two will cancel, and I'm just left with x. And the right-hand side is going to be, if I multiply these two together, remember, if you're multiplying a fraction by something like that, you're just multiplying the top line, because you're multiplying this fraction by sine 67 over 1. So the top line, the sine 67 goes above the line, the bottom line gets multiplied by 1 and stays the same. So it's 13 times sine 67 degrees all over sine 88 degrees. And again, making sure my calculator is in degree mode, because all the angle measurements here are given in degrees, I'll just pop the left-hand side here into my calculator, push it, go. The question says to give your answer to the nearest centimeter, so it comes out, when I put this into my calculator here, it comes out about 11.974, so to the nearest centimeter, that's 12. And to make sure, because you've got a unit of measurement here, make sure you include the unit of measurement or your answer is incomplete. So that missing third side there, so that missing second side is 12 centimeters. That's how I use the sine rule. So if you look at the second question then, on the question, the next page, question 4.2 on page 44. Again, we've got another triangle that looks like this. All right. And we've got an angle marked up here as 107 degrees. We've got an angle marked over here as 33 degrees. And we've got a side marked 7 here and a side marked x there. So can I use any of my right angle trigonometry? No, because we've got a 170-degree angle in there, so there isn't room for a right angle. It's definitely not a right angle triangle, all right? So I'm trying to pick between the sine and cosine rules. And can I use the sine rule? So I'm looking for a pairing. Well, you can see I know this angle here and the side opposite it. So because I do have a pairing, this question can be done with my sine rule. So I'll write the pairings as fractions, put the fractions equal, and solve. And again, whatever I'm looking for, I'll put on top. So because it's a side, I'm looking for the sides on top. So write the pair I know as a fraction, the side on top. So I get 7 over sine 33 degrees. Okay, that's that fraction written as or that pair written as a fraction. And here with the side on top, it's x over sine 107 degrees. Okay, and remember the sine rule means that those two sides, those two fractions are equal. So again, all I got to do now is multiply both sides by the denominator on this side here to remove it. So we multiply both sides by sine 107 degrees like that. With this side by sine 107 degrees there. Okay, and on the left-hand side, the sine 107 goes above, so I get 7 times sine 107 degrees over sine 33 degrees. On the right-hand side, these will cancel and just leave the x behind. So again, if I put the left-hand side there into my calculator, it says to give your answer to 1 decimal place, so it's about 12.291. To 1 decimal place, that's about 12.3. And because there's no units of measurement on this length here, there's no unit of measurement on my answer. So it might be worth pausing the video there and maybe just trying yourself the question on page 45, the next question on page 45, just to make sure you can do it. So you can see this is question 4.3 here. And again, is the triangle right angled? Well, definitely not. Because if I was to add these two angles together and subtract from 180, I don't get 90. That's not a 90-degree angle up there. That angle up there is 87. So 82 plus 11 is 93. And 180 minus 93 is 87. That angle up there is 87. Okay, I'm writing that in, as I'm sure you've done already, at the top. So that angle up there is 87. So it's not a right angle triangle. So I can't use any of my right angle trigonometry methods. I can't use sine, cosine, or tan ratios because the triangle is not right angled. So I'm trying to pick between the sine rule and the cosine rule. So do I have a pairing? Well, you can see, yes, I do. I do have the pairing here that I know the size of this angle and the length of the side opposite it. So I do have a pairing there. So I can do this question with my sine rule. All right. So then when I'm completing the other pairing, remember, it's not x and 11 degrees. They're not part of the same pairing. They're not opposite one another. So the side x is opposite this angle, and that side is opposite the other. So I couldn't make those two into a fraction, okay, to make up the other half of the equation, because they're not part of the same pairing. Remember, the pairings are made up of an angle and the side opposite it, okay? So that's why I do actually need that 87 up there, because that 87, which I can find just by subtracting the two angles I had from 180, is the one that's opposite the x. So opposite x there is the 87 degrees, right? So now I'll just write my pairs as fractions, sides on top, because it's the side I'm looking for. So 16.3 over sine 82 degrees. Remember, it's always the sine of the angle. That's why it's called the sine rule, all right? And then the other pairing, it's x over sine 87 degrees. And just even before I kind of do my calculation, it looks to me like these two angles are pretty much, very similar in size. So these sides are probably going to be very similar in size as well. Okay, so that's kind of what I'm expecting. So again, if I multiply both sides by the denominator from the right-hand side to remove it, so I multiply both sides here by sine 87. Okay, so to get rid of fractions. And on the right-hand side here, they will cancel and leave the x behind. So on this side here, I get 16.3 times sine 87 degrees over sine 82. And again, if I just put that left-hand side straight into my calculator, I get an answer. It's about 16.4376. It's about 16.4 to 1 decimal place. And again, it's got the same units of measurement as the side I was given, 16.4. So that looks about right. This angle is a little bit bigger than that one. So the side opposite is a little bit bigger than the side opposite that one. Okay, so 16.4 is the answer there. Now, if you look at question 4.4 on the next page, just when we're trying to find an angle, our method doesn't change in the slightest. So our method remains exactly the same. Okay, if I'm trying to find an angle. So in this case here, I've got a triangle that looks like this. right? So that's 85 degrees up there. And that's marked as theta. That's 10.5 there. And that's 13.5 there. Okay? So again, is the triangle right angled? Well, the correct answer is I don't know. It could be. That there's certainly room, if that's only 85, there's 95 degrees of angle left in that triangle. There could be a right angle. The fact that neither of these looks like a right angle is not conclusive. Okay, but because I don't know for sure the triangle's right angle, I have to assume it's not and proceed as though it isn't. And so I'm trying to pick between the sine rule and the cosine rule. Okay, so again, I'm checking, do I have a pairing? And you can see I do. I know this angle here, and I know the side opposite it. Okay, so I do have a pair. So because I have a pairing, I can use my sine rule. So again, I'm going to make the pairs, and I'm trying to find this angle here. I have to have the other member of that pair, so I can use my sine rule. So the only difference now is because it's an angle I'm looking for, I'm going to put the angles on top this time. So sides, if I'm looking for a side, I'll put the sides on top. Looking for an angle, I'll put the angles on top. Okay, so if I put the angles on top this time, so the pair I know, it's sine 85 degrees over 13.5. That's that pair written as a fraction. And then be careful, it's sine theta, not just theta, sine theta over 10.5. So there's the two pairs written as fractions. Remember, the sine rule tells you that those two are equal to one another. Okay? So now, as before, to remove that 10.5 on the right-hand side, I'll multiply both sides by that denominator. So I'll multiply this side by 10.5, I'll multiply this side by 10.5, right? And as always, they will cancel on the right-hand side. So I'm just left with sine theta. Okay? And over here, we get 10.5 times sine 85 degrees all over 13.5, right? And again, I'll just pop that into my calculator as it appears there, and that comes out at around about 0.7748. Right? Now, I'm going to keep that entire number on my calculator display screen. Don't just kind of approximate there. It doesn't really matter how many decimal places I write down here, but keep the entire number on your calculator display screen, because I'm going to use the answer button now to get my final answer. Because remember, that's what sine theta is equal to. And as we met back in lesson 3, to remove the sine from the left-hand side, I'll go with the inverse sine of both sides. So theta then is the inverse sine of 0.7748. That's the way I'm writing it down. But on my calculator, when I press the inverse sine button, I'm going to press my answer key. So when I press the button marked answer, so I put the answer in there, what that means is get the inverse sine of your entire previous answer, the entire decimal number. Put the whole thing in there. Okay, and if I press equals, it comes out about 50.8. And remember, that's a measurement in degrees. It's 50.8 degrees because that angle is in degrees, so the other one is in degrees as well. Okay, so the size of the missing angle there is 50.8. So look at the next question, the one on the next page. Okay. Next calculation. So it looks like this. You've got this triangle here, like that. Right, that angle there is marked as 98 degrees, so we know for sure this triangle is not right angled. Can't be. Okay, that's marked as theta. Okay, that's marked as 8, and that's marked as 5. So again, can't use any of my right angle trigonometry, so I'm looking for a pair to see if I can use the sine rule, and I can. I know this angle here and the side opposite it. Remember, that's what I mean by a pair, the length of a side and the size of the angle opposite that side. That's what makes up a pair here. I have a pairing. I'm trying to find, I've got the other member of that pair, the side opposite one I'm looking for. So again, we can set our sine rule up. So we just make the pairs into fractions, putting whatever you're looking for on top. It's not wrong to put it the other way around. Just there's an extra line in your solution. Just saves you a line if you put what you're looking for on top. So if it's an angle you're looking for, put the angles on top. Sides you're looking for, put the sides on top. Doesn't make any difference. It'll just speed you up. Okay? So it's an angle I'm looking for the angles on top. So if I say, look, sine of 98 degrees over 8, that's the pair I know written as a fraction. And sine theta over 5, and they're equal to one another like that. That's what the sine rule is. Those pairs are equal. And as always, to remove this fraction here, I'll multiply both sides by 5. And on the right-hand side, these two guys will cancel like that. And I'm just left with sine theta here. And then over on the left-hand side, the 5 just, as always, just ends up above the line like that. So it's 5 sine 98 degrees over 8. And I'll just put this into my calculator here, and it comes out around 0.6189. Again, it doesn't matter how many decimal places you write down there. Just keep the entire number on your calculator display screen and use the ANS button, the answer button, to put that entire number, not just the approximated version you got there, the entire number into the inverse sine function, right? So we'll take the inverse sine of both sides here. So theta then is the inverse sine of that answer there, 0.6189. We get the inverse sine of that, and it comes out, it says to 1 decimal place, so it's about 38.2 degrees. Okay, so kind of the final one of those sine rule questions then, it might be just worth pausing the video there and then have a look at page 48 and just check if you can do that question on page 48, and that sine rule calculation. So here's the question from page 48. So again, is the triangle right angle? Definitely not. So I'm trying to choose between the sine and cosine rules. And again, you can see I do have a pairing here again. So I know the size of this angle here, and I know the length of the side opposite it. So I do have that pairing like that. All right. Now, in this case here, notice that like the other example I kind of let you try by yourself, the angle I'm looking for is theta. I would need to know that side there. That's the other member of this pairing. So I can't make a fraction out of these two here because they're not opposite one another. When you're making these fractions, they have to be made of sides and angles that are opposite one another. So I'm just going to call this angle over here A for a second, because that's the one that's opposite the 7. And that's the one I'm going to be able to find using the sine rule. So anyway, this is a two-step calculation. I can't find theta directly because I don't know the side opposite that to complete that particular fraction. But I can find this angle here, and then by subtracting these two from 180, I can find the one I'm looking for. So it's slightly more roundabout way of finding it. So again, I'll make the pairs. So it's sine 124 over 17, and it's going to be sine A over 7. We'll multiply both sides by 7 to remove the fraction. Okay, like that. So I get that sine A is 7 times sine 124 over 17. If I put that into my calculator, that comes out at around about 0.3414. And then take the inverse sine of your answer to get A. A is the inverse sine of 0.3144, using the entire number there, and that comes out about 49.4 degrees, right? So this angle up here is 49.4 degrees, and that means then if I subtract the two angles I've got from 180, I've got theta, because the three angles of the triangle add up to 180. So theta then is 180 degrees minus 124 minus 49.4 degrees, and that's equal to it's about 19.96. Sorry, that's 19.96 there. Sorry, that's 19.96. That's about 20 degrees there. It's the nearest degree. That's about 20 degrees there. Sorry, that's a typo. So that's 20 degrees there, that angle. So that angle there comes out at about 20 degrees. So that one up there is 20 degrees, right? That one up there. So that means theta is 124, take away 24, and then take away 20. Okay, and that's 36 degrees is the size of this angle. Okay, so again, when you're using the sine rule, the important thing is to identify pairings and make those pairings into fractions, and then put the fractions equal to one another, and you can save yourself a bit of time if you put what you're looking for above. So one final thing to be aware of when you're using the sine rule is that sometimes when I'm using the sine rule to find an angle, there can be more than one answer. That using the sine rule to generate an angle sometimes does not produce a unique result. There's two possible answers. And this is referred to as an ambiguous case of the sine rule. So an ambiguous case happens, as you can see on page 42 of your notes. An ambiguous case happens when one of the sides can be swung around to hit the base of the triangle again within that triangle, on the same side of the side you're given. I'll show you what I mean by that now in a second. But an ambiguous case of sine rule is when there's two possible values for the angle you're trying to find using the sine rule, right? And when will this happen? Well, this will really only happen when the angle you find using your sine rule is bigger than the one that was given in the triangle you were solving to begin with. So if you look at all the examples of the sine rule you've done so far, the angle you ended up finding using your sine rule was smaller than the angle that was given in the triangle, right? So there's no ambiguous cases there. An ambiguous case arises when the angle you find using your sine rule is bigger than the one that was given the triangle, right? So that's when an ambiguous case arises. And the important thing is that the two answers you're looking for when you're dealing with an ambiguous case, they always add up to 180 degrees. Right, they're supplementary angles. So supplementary angles are angles which add up to 180, and the two solutions for an ambiguous case of the sine rule are always supplementary, that the two of them will add up to 180 degrees. So if you look, for example, at the question on page 49. So we've got this triangle here. Right, looks like this. And we're told that that angle there is 40 degrees. And this side here is 11, that side there is 13, and that side there is theta. And we're asked, it says, find two possible values of for the size of the angle marked theta in the diagram below. Give your answers correct to one decimal place. Okay, so we're trying to find two values for theta here. So again, notice it's the same setup. It's not it could be a right angle triangle, but I can't be sure. I do have a pairing, so it is a sine rule calculation. So I'll just make the pairs into fractions, putting the angles on top because it's an angle I'm looking for. So we've got sine 40 degrees over 11. That's the pair I know as a fraction. We've got sine theta over 13. That's the pair I don't know as a fraction. We just put those equal, and that's what the sine rule is. So we then multiply both sides by the 13, just to remove the fraction on the right-hand side. And I get 13 times sine 40 degrees over 11 is equal to sine theta. All right? And if I put that left-hand side into my calculator, that comes out at about 0.7597. All right, so then again, keep that entire number on your calculator display screen, and then theta is the inverse sine of that. 0.7597. And if I put that into my calculator, that comes out about 49.4 degrees. So that's one possible answer there, 49.4 degrees. So to find the second one, all I've got to do is subtract that from 180. Okay, so the second answer there, the second value for theta, it's 180 degrees minus 49.4 degrees, which is 130.6 degrees. So in this case here, they're the two answers. And notice the reason why we got an ambiguous case, the angle we found using our sine rule was smaller than the angle we found in the triangle. Okay, so that's when an ambiguous case arises. Okay, so if you look at the one on page 50 on the next page. Okay, so we've got this question here. It says, in a triangle PQR, you're given that PQ is 12, QR is 8, and the angle QPR is 38 degrees. It says find two possible values for the angle P or Q. So I'll just make a very rough sketch here, just to make sure I can see what's going on in the case of this triangle here. There's my triangle there. Okay, that's P, Q, and R. Okay, so that's 38 degrees there. Because we're told that's the angle QPR. Remember that it's where the middle letter is. So QPR, the angle's at the middle letter P. We're told that PQ is 12. So PQ, that side there is 12. And we're told that QR is 8. So QR is 8, that's that side there. And it says to find two possible values for P or Q. P or Q, it's here at or where the middle letter is. That's the angle we're trying to find. So you can see it's just another straightforward sine rule. Again, there's no way of knowing if the triangle's right angled. I was just drawing that sketch very randomly. There's the pairing. I know so I can use my sine rule. Okay, there's the other member of that pairing. So again, if I set that up as usual, so sine 38 degrees over 8, okay, will be equal to sine theta over 12. We'll multiply both sides by the denominator from the right-hand side. Okay, they'll cancel. And I get sine theta is equal to 12 times sine 38 degrees over 8. And if I put that left-hand side into my calculator, the answer I get there, it's round about 0.9235 or thereabouts. Okay? And then again, we'll take the inverse sine of that to find the size of the angle, 0.9235. All right, and if I put that into my calculator, that comes out about 67.442. It says the nearest degrees, that's 67 degrees. So that's one possible value here. And notice again, the angle we just found using our sine rule is bigger than the one we were given in the triangle. That's why we've got an ambiguous case here. So how do I find the second solution? Well, the second solution is just 180 degrees. Take away the one we've got, take away the 67, and that's 113. So there's my two solutions. 67 and 113 are the two solutions I'm looking for. Okay? So that's the ambiguous case. Okay, so just trying to try and illustrate the ambiguous case here, that I'm just going to draw more accurately the triangle from the question we just did, the one on page 50. All right, so remember that's the basic sketch of the triangle there. So I just got my ruler, drew that line there, got my protraction, measured that 38-degree angle accurately. There's a 30-degree angle here. I just set my compass to 12 centimeters. Okay, just marked a point here. So I've got the points P and Q. So I just have to find OR. And where OR is down here on this base somewhere, and it's 8 centimeters away from Q. So all I'm doing there now is I'm setting my compass to 8 centimeters, right? I'm going to put the point of my compass here, okay, on Q, like that. And then just from there, I'm just going to sweep it around. You can see, okay, oh, okay, there we go. So you can see if I sweep it around like that, this side here, the compass hits the base in 2 different locations. So because that angle there is so narrow, when I sweep it around here, I can hit the base of the triangle in 2 different places. So there's 2 different places I could put the point OR. So you can see if I join these 2 together here, like that, where that side there is 8. So that fits the description given in the question purpose. So there's a location for OR. And notice, in that case, the angle theta here, you can see that's clearly an acute angle. That's obviously the 60-degree angle we found as one of our answers. That's a smaller one we found. But I could also, this point here is also 8 centimeters away from Q. So if I join those 2 together there, that's also 8 centimeters. That one there, right? So that's 8 centimeters there as well. So there's another part, and you can see in this case here, that's the bigger one there, that's the larger one. And this, like, you can kind of maybe see now why the 2 angles are supplementary. Because if these 2 sides here are both 8, because they were drawn with the same compass radius, it means that side there and that side there are the same length. So this triangle is isosceles. So if that's 60, so is that one. So how then could I find this angle here? Well, because this is a straight line here, subtract 60 from 180, that's where we get our 120. Okay, so that's why the 2 angles are supplementary. You can see they do make a straight line down here at this end. So you get an ambiguous case when one of the sides of the triangle can be swung around to hit the base of the triangle twice. And it's only going to happen using the sine rule when the angle you find using your sine rule is bigger than the one you were given in the question. If you compare that to the question we did back on page 46. So there's the triangle from page 46. You can see we've got the 85-degree angle here. We've got the 10.5 side that way. Same kind of idea. Trying to draw that triangle accurately. And the third side, remember, is 13.5. So I've now set my compass to 13.5 centimeters this time. I'll put the point of my compass up here. And you can see if I sweep it around, oh, okay. Right, so it looks like this. So this time, when I hit the base twice, this one you can see out here, if I join those 2 together, it's outside. That 85-degree angle is not inside the triangle anymore. So that's not going to produce a triangle with 85 degrees in it. That one doesn't fit. But if I join these 2 together, like that, there's the one and only location. There's the angle that we found using our sine. There's the 50.8-degree angle down there. Okay, and that's because this angle here is quite wide compared to the one that we found. So the ambiguous case happens when it's possible to swing one of the sides around and hit the base of the triangle twice. And we've also kind of illustrated why the 2 angles are supplementary, why they add up to 180. So to finish off this lesson, it might be worth just pausing the video there and just try the final calculation, the one on page 51, and the final sine rule calculation. Okay, so we're told the triangle ABC. So I'll just draw a quick triangle ABC here. Just a very rough sketch just to see what the information I'm given is. ABC like that. We're told that AB is 11.2. That's 11.2 there. AC is 5.8. So this one here is 5.8. And the angle ABC, it's going to be where the mid letter is ABC. That's this one there, is 26.6 degrees. Okay, we're asked to find 2 values of the angle ACB. That's this one here. Okay, where the letter C is. Okay? So again, it's the same as all the sine rule calculations we've done so far. I don't know if the triangle is right angle, but there's my pairing there. So I can just set up my usual sine rule. I'll say that sine 26.6 degrees over 5.8 is equal to sine theta over 11.2. Okay, and then we'll multiply both sides by 11.2 to remove the fraction on the left-hand side. They will cancel, and I can just get sine theta here is equal to 11.2 times sine 26.6 degrees over 5.8. And if I put that left-hand side right into my calculator there, okay, that comes out at about 0.8646. Okay, and then again, theta is the inverse sine of that number. So I'll take the whole number, you just inverse sine of my answer. Use the answer key on your calculator to throw the whole number in there. And that comes out, it says the nearest degree, it's about 59.8. So the nearest degree, that's 60 degrees. That's one possible answer. And because we were asked for two, again, because the angle we found using our sine rule is bigger than the one we were given in the triangle, okay, to find the other angle, theta then is 180 degrees minus 60 degrees, which is 120. So there's my two answers, 120 and 60. And then part two, kind of a little bit of a head scratcher. It says, in the space provided below, draw a sketch of the triangle ABC showing two possible positions at the point C. Well, I kind of did that a moment ago. That if I was trying to sketch that triangle a little bit more accurately, right? So there's the base of my triangle like that. Okay, this horizontal line here. I'd get my protractor out, break out the weapons of maths construction, and get your protractor to measure 26.6 degrees. Okay, so we'd have our 26.6 degrees there, right? So that's our point B. We'd set our compass to 11.2 and just mark a point up here. So that's 11.2 there, and there's our point A. And then to find C, we would then set our compass to 5.8. And wherever our compass hits the bottom line here, we're going to get, we find our point C. So again, the compass would probably do something like that, right? So you can see I've got one option here and one option here, like that. Okay, just two possible locations there. So C could be here and C could be here because they're both 5.8s. Like that, okay? And you can see, if C is here, then obviously that's the acute angle. That's going to be that one there. That's the 60 degrees there, okay? And then if this angle here, that angle there is the 120. So that angle out there is 120, okay? So there's the acute one and the obtuse one, okay? So that's just a very rough sketch of that. Just two different locations there, both places where the point C can live. So that's how we use the sine rule to find sides and angles and how we deal with the ambiguous case. Very quickly in the next lesson, we're going to put the final tool into your toolbox, and that's using the cosine rule. The cosine rule is the technique we'll use if we're trying to solve a triangle like this when we don't know for sure it's right angled and we don't have a pair. So we'll cover that in our next lesson.